How you doing? Hope you're having a good day. Today we'll be discussing phase and group velocities, and we'll be thinking about two waves. Keep things simple before we go on too many waves. So imagine we have two electromagnetic waves. We're going to call the first wave E1, and we're going to say that it has some amplitude, E10, and a time varying term, sine k 1x minus omega 2t minus omega 1t, and we'll have E2 is E2 naught sine k2x minus omega 1t, omega 2t. Keep getting that one wrong. Okay. If it has the subscript 1, the k has the 1, the omega has 1. Okay. Now, what we're going to assume throughout the video is that the waves are nearly monochromatic, so that K1 is nearly equal to K2, and E10 is nearly equal to E20. So, we can just rewrite E2 as approximately E10, because their amplitudes are going to be equal. Sine K2x minus omega 2t. Okay. Now, if we interfere these waves, there's going to be a new electric field produced, E3. That's going to be E1 plus E2, and it's going to look like E10 sine K1x minus omega 1t plus sine K2x minus omega 2t. Okay, and here we're going to use the trig identity. It says that sine of u plus sine of v equals 2 sine u plus v over 2 sine cosine u minus v over 2. Okay, so the u is going to be this part, the v is going to be this part. And so I'll just rewrite E3 using this trig identity. Okay, so I just rewrote E3 using those trig identities, and this is what it turns out to be. Okay, now the velocity of the waves is given by the frequency divided, so the thing in front of the t divided by the wave number, the thing in front of the x. So we see that we have two different velocities here. One of the velocities, the 2's are going to cancel, so I'm going to ignore those. One of the velocities is omega 1 plus omega 2 over k1 plus k2. Another velocity, v2, is omega 1 minus omega 2 over k1 minus k2. And we assumed that our waves were nearly monochromatic, so that, in other words, that's going to say this V1 is the average of the velocity of the two initial waves. So, in other words, we'll just write omega over k, where omega is the average frequency of the two waves, k is the average frequency of the two k's. And then V2, we're just going to write as delta omega, the difference in the frequencies divided by the differences in the k's. So, essentially, we got two velocities out of that. We had two velocities before, and those were both phase velocities. So if you were to view each wave, not looking at the other wave, the first wave would have been moving at omega 1 over k1, the second wave would have been moving at omega 2 over k2. Essentially, that's nearly the same speed, because of our assumption that they're nearly monochromatic. So what that is called the phase velocity, and that's v1. Another thing is called the group velocity, and that's v2. And I'm going to help illustrate this by showing you a Mathematica animation. Okay, so here we are in Mathematica, and here I've plotted 3 different waves. One of the waves is sine k1x minus w1t, I'm calling omega w here. And another wave sine k2x minus w2t, and then the third wave is just the sum of those. And you can see the legend here. It denotes which color is which wave. And what we're looking at is the wave propagating through space. I can freeze time if I want, but the horizontal coordinate is the spatial coordinate here. And I'm also calculating the phase velocity, and I have those calculations up here. So the first wave travels with the speed omega 1 over k1. The second wave travels with omega 2 over k2. And the sum of those 2 waves travels with the average frequency over the average wave number. And the group velocity is the difference in the frequencies divided by the difference in the wave numbers. And so that's how I'm calculating these up here. Okay, so notice that when I hit play, you see this enveloped sort of almond-shaped thing moving at a speed greater than the individual waves are moving. So you can see how fast the green and the orange waves are moving. I'm kind of following a green wave with my mouse right now. And the almond-shaped packets are traveling much faster than that. And it's hard to do here, but if you could pick a point on this blue wave and follow it, it'd be traveling a little bit faster than the green wave, but it'd still be going slower than the envelope, because that's the phase velocity total I'm talking about here. And there's a few interesting things to note when you're learning about group velocity, phase velocity. So you can, if you have a group of waves, say electromagnetic waves, that group of waves can travel faster. That can have a group velocity faster than the speed of light. And I'm kind of illustrating that case right here. So if we have a couple of different colors of light, wave 1 and wave 2, and they interfere, well, the interference pattern can travel faster than speed of light. But I'm not really sure how all that works. I don't know if you can send information faster than the speed of light. I don't think so, but I just know that the group velocity can be faster than the speed of light. And in that way, you can have indices of refraction, which is c divided by v, where v is the speed of, v is the group velocity. So since the group velocity can be bigger than c, you can have an index of refraction less than 1. And, interestingly, you can also have negative indices of refraction, because you can have negative group velocities. So if we make k1 larger than k2, now we have a negative group velocity. So the envelope's traveling to the left, while all the other waves, phase velocity included, are traveling to the right. And we can pretty much freeze our group and make a sort of standing wave by setting the frequencies equal to each other. So now we have a group velocity of 0, but you see these individual peaks inside the sum wave are still traveling forward, but the envelope is staying stationary. That's sort of like when you pluck a string on an instrument, it can have many different modes going through it, the modes being the wave 1 and wave 2, but you'll only hear one frequency, which would be the sum. Well, the frequency you hear would be the difference of all the modes. Okay, so, and the group velocity is like the standard wave pattern. Okay, so what else is interesting about this? Oh, so let's set k1 equal to k2 so that we have an infinity in the denominator. Okay, well, let's make the omegas different, and we see that something weird happens here. The amplitude of the sun is getting modulated. I can't really explain why that happens. I don't know that much about it, but that's interesting. It's probably something to do with instead of writing our signs, if we wrote it as complex exponentials, we could probably understand the behavior why it's doing that. Okay, so now I just want to mess around with a few other things, see what happens. Well, first let's change the k's again, and let's make omega 1 much larger than omega 2. Okay, so we see the group velocities flying. But besides that, not much else changed. The envelope has the same shape, no matter what we do with the omegas. Okay, and if we mess with the k's, let's make k1 smaller, we see that our envelope sort of decreases in width. Keeps decreasing in width until essentially you're just going to mimic one wave. And now, remember we had the assumption that the two waves were nearly monochromatic. But now I've changed k1 so much that it's not even close to k2, so the waves are not even close to nearly monochromatic, so our approximation breaks down, and that's why you don't really see the group velocity and phase velocity behavior within this. I mean, the group looks like it's traveling at the same velocity as wave 1, yet the numbers don't come out even close to the same. So I think that's because the approximation we made that they're nearly chromatic breaks down. Anyways, that's just a little bit on the behavior of group velocity and phase velocity for the case of two waves. Now we start to see some more complicated but more interesting behavior when we have many waves. And I'll talk about that in the next video. Thanks for watching and have a great day.